So, welcome everybody. It's a great pleasure to introduce the speaker of today's MOX colloquium. So Professor David Keys is a senior associate to the president of the King Abdullah University of Science and Technology and a director of the Extreme Computing Center at KAUST. He was the inaugural dean of the Division of Computer, Electrical, and Mathematical Science and Engineering at KAUST. He studied in the US. He graduated in aerospace and mechanical engineer and mechanical science from Princeton and received his doctoral degree in applied mathematics from Harvard. So he's a world leader and gave pioneering contributions to the algorithmic interface between parallel computing and the numerical analysis of partial differential equations with a focus on scalable solvers for emerging architectures. And they are used in many large-scale applications in energy and sustainable development. You have a very long list of prizes and recognitions, so let me mention just a few of them. He is a fellow of SIAM, a fellow of the American Mathematical Society, and he shared the Gordon Bell Prize in 1999. So it's a great pleasure, and thanks for accepting our invitation. So please, the floor is yours.
Thank you. Essendo per me italiano, dividerò la mia conferenza in due parti. La prima in italiano e la seconda in inglese. Bene, veniamo alla seconda parte. I wish Alfio were here because he taught me that translation way back at the Como domain decomposition meeting. And I hope if he picks up this video, that he will appreciate the lasting legacy of the Como meeting beyond all the algorithms. And I really am half Italian, ancestors, grandparents from Firenze. But I unfortunately don't speak the language other than what you find in musical directives. But it's a deep honor to be at the MOX colloquium. I know, the heritage of speakers that have been here and all the creative mathematics that have come out of here, including we were just talking about the America's Cup with Nicola, that modeling, which is one of the most famous, but maybe the deeper ones in terms of functional analysis and scalable solvers are all well known. And I do look forward next week to having 4 Italian keynote speakers at the domain decomposition meeting number 28 in KAUST in Saudi Arabia, including Gabriele. So I offer a choice of topics, and the one that I found resonated, not surprisingly, since Italy now has so many supercomputers in the upper ranks, including 2 machines named Leonardo, and the machine at ENI, and I think a whole bunch of Eviden machines that you're very interested, and you should be, because these supercomputers soak up a lot of energy. The supercomputer we have at KAUST is equivalent to 13,000 Saudi citizens of average, energy use every hour it's running. And so the topic was efficient computation through tuned approximation. And the first thing that I wanted to ask when I got here was the origin of the word MOX, what you call someone who belongs to MOX. And I found out that in English it's Moxian. And the reason that that was of interest to me is because where I come from, there's a classic drink called Moxie. So I would like to consider myself a Moxie in your presence today. So getting serious, what is extreme computing? It can mean many things, actually. One of them, the most common one, is an extreme scaling of the resources, especially the number of nodes, stacking up nowadays exaflops. But another extreme is present in almost every CPU, like the new 96-core AMD Genoa. There's a lot less memory bandwidth per core than there should be for a balanced algorithm. Another extreme in GPUs is there's a lot less memory per core. GPUs major on the memory bandwidth, but they don't give you that much memory. So you have these two choices, both of which I consider, growing to extreme in the sense that we have to, balance old algorithms, which have, not so many flops per byte moved in these memory limited architectures. So even one node can be an extreme computing. Another extreme is low power constraints, like edge devices that have to run on batteries, or things that are like a telescope on a mountain that doesn't have a power source. Another is real-time constraints. That can be extreme, like streaming apps, like decoding wireless or collecting data from an experimental system. Another extreme, which is sort of pedestrian, is just all these apps that don't scale that well, that have like 2-week running times, like some density functional codes. So for these various definitions of extreme, the research group that I've been privileged to lead at KAUST has worked on a large variety of software, and some of it has made it into commercial or research use, like the K-BLAs, which filled in some missing pieces in the Q-BLAs until they were eventually adopted by NVIDIA. The KSVD, which used Nick Hyam's polar decomposition, which has an arbitrary amount of concurrency. You can keep doing bisection and not be limited to the concurrency down a diagonal conventional SVD solvers. It does a lot more flops than all the conventional SVD methods, but because it's so highly concurrent, and it can actually finish in less time on a massive machine. Gira is a Cartesian mesh thing for multi-core, multi-cache architectures that doesn't just do the simple thing of one piece of the cache for each core, but many cores sharing a piece of the cache to do, basically reuse one mesh point in several time steps before it has to go back to DRAM. And MLBS is a multi-level buffer system. These are both used in Aramco's seismic imaging. We have an R interface on our max likelihood estimation of spatial statistics. We are on Sky with multi-objective adaptive optics in the Japanese telescope in Hawaii, sort of deconvolving atmospheric turbulence from observations. One of our PhD graduates in hierarchical matrices implemented on GPUs was hired by Sherry Lee at Berkeley to be part of the StrumPack project. We have seismic and other optics things, and not all of them, of course, have made it into maturity, but this is the direction that we have been focusing. And I'll end up with a couple of applications that were recent Gordon Bell finalists. But I first wanted to mention that besides all these extreme things, we do some conventional library development too, like PETSI. And I'm very proud to say that almost from the beginning of my time at KAUST, I've been the proud employer of Stefano Zampini, a student of Luca's who's listening from Milan. And Stefano certainly, I think he's the 4th largest contributor to lines of code in PETSI. So my conclusions up front, in case you have to leave or if I put you to sleep, are that we must address the need for greater efficiency when we take delivery of these massive machines. It's not a time to get lazy because we have so many resources. It's a time to work harder because we have so many resources. And as a community, we have historically succeeded in all 3 of these different dimensions of efficiency: better architectures, more efficient use of applications, especially redefining what are the outputs of interest so we don't overcompute, and algorithms, and that's where I'll focus my talk. And in particular, on 2 new algorithmic opportunities: reduced rank representations on a block-by-block basis within matrices, and reduced precision representations, again, not necessarily overall, but adaptively using multiple precisions within the same code based on, in some cases, some rigorous estimates of the precision that you can get away with while still getting a high precision result. Our journey began with a comparison of these 2 executions. I think this was on, this was 128 cores, 432 nodes of a Cray XC40. And this was a tiled Cholesky factorization related to spatial statistics. And the conventional algorithm in a runtime-based directed acyclic graph, efficient implementation from the Don Guerra group or the French group took about 18 seconds. Our version took about 1/10 that amount of time, because we were able to replace most of the dense blocks in that huge 54K by 54K covariance matrix with low rank equivalents without losing accuracy in the result. Now, there are many things that parallel scaling people don't like about this way of doing things. It scores a lower percentage of peak because it's squeezed out a lot of flops and memory transfers. It has a poorer load balance. There's a higher percentage of idle time because of the adaptivity. It scales less efficiently from 1 to 128 cores than the full flop-rich one. And however, despite those three, normally these would be votes against an algorithm in a parallel performance context, but you can't argue against the 10x improvement in runtime for an application that not only finished earlier, but while it was executing, used about 65% of the average power. So it's about a 15x improvement in efficiency for getting results that the statisticians were equally happy with. And this led us on a path with two swim lanes, one of them to adaptively, well, at first in a brute force way, and later in an adaptive way, replace dense blocks with low rank blocks, and another to replace full precision blocks with lower precision blocks. And now we have these data structures, which we think are unique to us, where this is actually one matrix. You can multiply with it, you can Cholesky solve on it, and so forth. But in sort of an operator overloaded way, every pair of blocks that interact, it takes into account their rank and their precision in order to operate correctly within the overall context. So we consider this a renaissance in numerical linear algebra that says don't oversolve, maintain just enough accuracy for the application purpose, and economize on storage, because ultimately many multiple precision algorithms keep a copy of the matrix in each precision, like the classic iterative correction Gauss elimination. So I want to consider these three categories of efficiency improvement from architectures, applications, and algorithms. But at the end of the talk, I'll talk about our 2022 and 2023 Gordon Bell finalist papers, one in spatial statistics and one in seismic imaging. Talk about efficiency improvements in kernel linear algebra operations from exploiting rank structure and precision structure. And the motivation, which again should be shared by Italy because of all the very high-end machines that you operate on behalf of yourselves and the European Union, addressing the energy elephant. The top machine in the world delivers 1 exaflops, but at about 50 gigaflops per watt. That means that it is, that means it's consuming 20 megawatts continuously at a representative electricity cost of 20 cents per kilowatt hour. That's $200 per megawatt hour, which means it's 4,000 US dollars per operational hour. There's approximately 10 kilo hours a year, 8,760 to be exact. That's $40 million of electricity bill. But let's talk about the carbon footprint. At about half a kilogram CO2 equivalent per kilowatt hour, this is 10,000 kilograms CO2 per exaflops, which is 100,000 metric tons annually, which is equivalent to the average driving of 20,000 passenger cars in the USA with miles per gallon and miles driven per year. So if you could get a 10% improvement on, say, some kernel like dense linear algebra that dominates your application, you're saving $4 million a year and taking 2,000 cars off the road. If you can get a 10x improvement, and I showed one, right? That would be 36 million a year and taking 18,000 cars off the road. And 10x is achievable in many cases. So you have a choice: a supercomputer like Frontier, or a lot of other consumer attractions. So science per joule is a matter of planetary stewardship. And just to make an analogy that may hit closer to home for scientists who travel around the world giving talks, if you look at the passenger hour of commercial cruise, it's about a quarter of a metric ton of CO2 equivalent. So 1 hour of exaflops is like 40 people flying for about an hour with average cruise on a commercial airliner. And so these 39 passengers cost the same per hour as running frontier. So justify your next flight by efficient programming, or even better, justify mine here. So to give this talk. Okay. Now I said architecture. This is my one slide on architecture. It's a very impressive slide. It looks at the machine which was number one on the green 500, which is a subset of the top 500, where it's not just the gigaflops measured, but the gigaflops per watt while doing the linear algebra benchmark. And that has gone up by a factor of greater than 15 in 10 years. And this one is actually the frontier. So the number one machine in the world is actually using the most efficient hardware solutions, which I think is very nice. Let's talk about my one slide as giving an example of application efficiency. Let's say we want to compute the convective heat flux across a solid fluid boundary, like cooling some chips in a cavity of a computer. So this is some temperature contours. This would be an adaptively refined finite element mesh to get some nice precision, like 10 to the minus 6th. This would be a finite element mesh which gets, and so from this, of course, you take the normal derivative and integrate and get a scalar from all of this PDE solved everything. This mesh gives you the same answer to within 1%. Engineers are going to design conservatively by much more than a margin of error of 1%. So you could argue that the engineering interest in solving this problem could be satisfied by this, rather than this. This you might actually want a high accuracy solution in many cases, but very often a much coarser thing could be used for lower fidelity surrogates in early iterations of some nonlinear problem or some optimization problem. And these are ways to think of more efficient application uses. Algorithms is the rest of the talk. And as a paradigm for algorithmic improvements, we could consider the Poisson equation from the time that Gauss elimination was shown to be stable by von Neumann and Goldstein. And if you had a little cube and you used a natural ordering of that cube, the storage would be n to the 5th with the fill of the bandwidth from n cube points with an n squared bandwidth. And the flops would have been n to the 7th, where n is the dimension of one side of the cube. Then we had iterative algorithms, optimal SOR, which reduced both the storage and the flops considerably. And then there were incremental improvements in iterative algorithms until we had full multigrid, which prints out the answer in the time it takes to solve the problem, namely order n cubed, and only needs one copy, if you will, of the field, order one copy. So going from here to here on a mesh as small as 64 cubed is a factor of 16 million. There are about 31 million seconds in a year. So this algorithmic improvement is equivalent to reducing half a year of computing to 1 second on the same computer. That's math. And you can graph that on a Moore's law plot. Moore's law doubling performance every 18 months over a 36-year period is the dashed curve. For a small 64 by 64 cube, algorithmic improvements keep up with Moore's law. As the cube gets bigger, they dwarf it because we're improving the exponent in that. So in 2003, as part of the US SIDAC program, I was asked to interview something like 300 DOE scientists on their use of supercomputing to try to produce other algorithmic Moore's law. They were getting bored with bringing the Poisson equation to Congress to get money. So one example was this plasma fusion simulation group, where this is Moore's law in blue. And so you're tracking Moore's law in the hardware in stasis periods, but there's punctuated stasis where you're actually improving the algorithm. And the red one is for particle codes, and the green one is for MHD continuum codes. And that's one example. Another example was the Berkeley combustion group. Again, Moore's law is this plot on a log-lin curve. And these are some of the improvements in the chemistry and in the fluid dynamics that shifted us to a higher level. And so these are good examples of algorithmic efficiency improvements. And through the decades, we know of many algorithms that have replaced n's with log n's or better. The famous FFT, n squared to n log n. Multigrid, this was the number I quoted earlier for Poisson on a cube. down to n. Fast multipole, the summation of interacting gravitational or potential particles from n squared to n. Sparse grids representing a d-dimensional domain at a resolution of 1 over n by replacing all but one of those powers of n with a log of n with strategic placement of those points, assuming the solution is continuous. H matrices, solving a problem in order n cubed Gauss down to n log squared n, where k is the typical rank of the block. If the block is of order n, you don't win. You've done extra work. But if the k is much less than n, this is a huge win. Multi-level Monte Carlo, replacing n to the 3/2 with n log squared of n. Randomized algorithms replacing SVDs, for example, from n cubed to n squared log k, where again, k is the rank where you're allowed to truncate your SVD. And I always pose when I give talks like this when there are students in the room. Okay, so I'm waiting, what's the 2020s going to bring us? It might be something, I don't know, in machine learning. That's where a lot of improvements are needed today. So to summarize, architecture, application, algorithm, software. In a good world, these are orthogonal. You can take advantage of all of them. And let's talk now more about the linear algebra part. And one nice problem to refer to all the time is the potential problem. Here's the 1D Laplacian. And it's particularly important to think about it because being habituated by solving this problem, we've always asked for double precision in scientific hardware. We didn't adopt GPUs for many years after they were born until they started offering hardware double precision, largely because of the ill conditioning of the Laplacian. And indeed, it is an ill-conditioned system. As you know, the condition number grows like the square of the resolution, or 1 over the mesh spacing. And therefore, in single precision arithmetic, kappa approaches the reciprocal of the machine epsilon for as n as small, the condition number for n as small as 1,000 by 1,000. That's a small mesh today. Single precision wouldn't be acceptable there. The biharmonic gives out at even double precision at that size. So some multi-scale codes really do require high precisions, often available only in software, like double-double. But there are many cases where lower precisions will be acceptable, or we're not, inverting Poissons. And another thing you can illustrate with the one-dimensional Laplacian is the prevalence of low rankness in practice. A is full rank, but almost all of its subblocks are trivially low rank, like that corner. But what's interesting is that the inverse of A, though fully dense, is also trivially low rank in almost every block. You can envision that by noting that the columns of the inverse are basically the Green's functions at incremental points in that unit interval, and these are very low rank kind of things, right? So we actually find in many dense systems trivially low rank, and that's something that can be exploited in integral equations, like with fast multipole, covariances in statistics where there's a decay with distance, sure complements in PDEs. The PDEs are sparse, but when you start eliminating, you get sure complements that have data sparsity, even though they're dense. Hessians from PDE constrained optimization inherit that property from the underlying PDE. Non-local operators from fractional differential equations have low rank character. Radial basis functions from unstructured meshing, and kernel matrices from machine learning. Harder to find that structure there. Working on it, many people are. But you have to have a good ordering to find it in some of these cases. But basically, a lot of dense problems really could be represented like that. And a lot of them can also have blocks that can be replaced with reduced precision. There are famous multi-precision algorithms like iterative refinement, but there are many new algorithms. Chaim and Mary have a review article which uses up to 5 precisions in active numerica. And we've used as many as 3 in our work. And these ideas can be combined. So here's a data structure like the one I showed you earlier, a real one in this case, where this million by million dense symmetrics covariance matrix would take 4 terabytes to store using symmetry in dense double. So million times million, 10 to the 6th, 8 bytes, half of that, 4 terabytes. Its replacement with this hybrid data structure with different blocks of different types is about a quarter of that. So you can solve a 4 times bigger problem in your GPU, for example. And there's, I would say trivially, there's computational savings, but the main thing is the memory footprint is smaller, so there's data motion savings. Now, yes, the data structures are more complex, they're adaptive, they're harder to load balance, harder to debug, but the cost of energy is something that may justify it in many cases. What about the complexity of these rank structured factorizations? The straight LU or LD transpose is order n cubed, storage n squared. The tile low rank is replacing one of those n's with a square root of k, or a 1/2 power of n with a square root of k, where k is the max block rank. The fully hierarchical load rank, a la Hackbusch, a la Chertychnikov from the turn of the millennium, gets you down to this order n operations, order n storage. Again, this is not true for random matrices. This is true for a lot of matrices that come from physically causal systems like potentials and so forth. So rank is a tuning knob in finding efficiency. Replace dense blocks with reduced rank, high accuracy to build exact solvers, low accuracy to build preconditioners. Hardware parameters are something that you want to hit by investing this degree of freedom K. Maybe you want to pick your block size to match a cache capacity or a number of threads in a warp some way. So it gives you a way of adapting to ever-changing physical parameters in the architecture. And there's a wide variety of algorithmic tricks to find these low-rank things. It's typically at the innermost, it uses some small dense matrix multipliers, not the original dense block, but little dense blocks from the SVD factors. That's something that vendors optimize for us because it's important in machine learning. So you're riding a trend that other people are doing the hard stuff on, and you implement in batches of these blocks. There are many algorithms now. SVD is order n cubed. Randomized SVD I showed you earlier, n squared log k. There's a less accurate method due to Bebendorf, which is called adaptive cross approximation. And there's matrix skeletization, where you select a subset of rows, a subset of columns, then construct a small matrix in between to try to reproduce the original matrix as accurately as possible. We find these two aren't sufficiently tunable, like this one, for our guaranteed accuracy purposes, but they are attractive, even more efficient methods. With such algorithms, you can attack the memory capacity constraints, like spatial statistics or PDE constrained optimization. You can attack the power constraints, the real-time constraints, the running time constraints. These all lead to dense matrices with a certain amount of structure, many of them even being symmetric. And here's an example from spatial statistics, which led to our 2022 Gordon Bell submission. You have a number of points, so if you will, train your statistical fit. Your statistical fit has only a small number of parameters because you use some physics instead of just random parameters in a neural network to define it, but you still have to reproduce those the missing data at other points where you don't have measurements. And this leads to evaluating a log likelihood function where the parameters of the statistical fit are theta, L is like a loss function, Z is a vector of observations, and sigma is the covariance matrix. And you want to minimize this function L with a sort of low dimensional scalar optimization algorithm, but each step of evaluating L of theta involves maybe inverting a trillion by trillion matrix or log of its determinant, which can also be obtained from Cholesky factors. So here are a couple of random distributions in 2D, 3D, and the kernel here is just a decaying Gaussian. And this was a test case for the classical algorithm, which is order n cubed. These are 3 generations of Intel hardware. And the same 3 Intel chips were applied for the low rank algorithm. They go out further in memory because they need less memory per matrix size. And they have that n squared scaling asymptote. You can wait for hardware to improve, or you can use the same hardware and use a better algorithm, or if you're a scientist over a long career, you see both improvements in this kernel. That was the complexity. What about the memory size? That black bar is 4 terabytes for a million by million problem. The synthetic matrix we showed, if you want to improve the accuracy, like 10 to the minus 12, you're still saving an order of magnitude. You might be willing to save 2 orders of magnitude with a lower accuracy. And this one is from a real, I think, soil moisture max likelihood estimate. That was all shared memory. What about distributed memory? So we have a big Cray machine, and you could run scale-a-pack, conventional direct LU method, on, let's say, 16 to 256 nodes, going from the light blue to the dark green. Or on that same 16-node cluster, you could run the tile low rank version and beat all the higher node count runtimes at a given problem dimension. This is an extreme tile low rank, extreme because it was 42 million by 42 million. You can't solve that on this computer. It's not enough memory and you don't want to run it. But you can do, it would take 77 days and it would require 7 petabytes of memory. But you can run it with tile low rank and finish in a day or so. And these are the times based on, remember, degrees of freedom for that. Again, that's squared exponential in 2D and 3D. That, by the way, that dense calculation would have cost about $1 million of electricity. So 2 motivations for mixed precision, so much for low rank. One motivation, which may seem trivial, is that it's much better than no precision. Statisticians faced with covariance matrices that big often just assume things sufficiently far away have no correlation, essentially zero out many bands of the matrix. So in this case, low rank wins when you have things that are smoothly varying. Mixed precision wins when you have some blocks that are simply small magnitude compared to some other large blocks, so that when you combine them additively, the mantissa of the smaller one just falls off the end and needn't really be stored in the first place. By exploiting the allowable precisions, you can have a great energy consumption efficiency. And here are 3 generations of NVIDIA hardware. The Volta, like you have in the old the ENI machine, the Amperes like you have in the current Leonardo machines, and the Hopper, which is coming. And these are the years of these releases. And if you go from FP64 to FP16, you might think you would get a factor of 4 because you're moving 1/4 the amount of data. You actually get a factor of 8 because of the hardware optimizations. And with the 2 later generations, they have engineered it so that you win a factor of 16 by going from single to half. And in machine learning, you can use half. The question is, how much can you use half in scientific computations? This one doesn't have any of the animation, and it's upside down. You have teraflops instead of runtime. So up is good. And these are 3 generations of NVIDIA hardware, Pascal, Volta, and Ampere, and the different algorithms, the mixed double and half precision, and then fully double. So you can see, about a factor of 5 coming from the advances in hardware, and about a factor of 2 coming from advances in the algorithm over that period of time. So the savings, the relative ratios available from mixed precision are much less typically than low rank in these causal type problems. So that brings me to our 2022 Gordon Bell finalist paper, which was on geospatial statistical modeling. It was actually done with Jack Dongarra's group. This was before he was Turing Award winner. And people from my group and two of our statistics faculty. By the way, Mark will be in this room in September, I think. And maybe he'll tell much the same story. But these are, there's a spatial, a 2D spatial distribution and a 2D plus time distribution that we used in our demonstration. And you know, this is, we call this statistical emulation as opposed to, you know, simulation with PDEs. And there are many demands for more efficient weather and climate predictions in this way. They drive a lot of the supercomputing workload and waste a lot of energy predicting the climate by changing it. And, you know, they're usually memory bandwidth bound when they're on the statistical side. In the PDE side, the PDE simulations are memory bandwidth bound. They have sparse Jacobians. On the other hand, the covariance, the statistical versions are compute bound. So here's the challenge. You collect P observations at n locations. You want to find an optimal fit to some plausible function and infer missing values of interest. The max likelihood method is a optimization method for tuning those parameters. Its complexity comes in the inversion and the log determinants of the covariance matrix, and the memory footprint, you know, is huge for the number of measurements that are available today. Dorrit Hammerling, a leader in the spatial statistics domain when it comes to weather, basically complained about 5 years ago in a national international meeting on this, that you know, we don't really have tools to work with spatial statistics on irregularly spaced data. And again, if n is a million, and storage is a trillion, but you know, the number of flops is an exaflops, not the rate, the number of flops. So traditional approaches are to you assume global low rank, which is really physically not acceptable, or to zero the outer diagonals. Better approaches are to exploit hierarchical low rank off the main diagonals and reduce precision outer diagonals, as we've seen. And you know how big 4 terabytes is and how long it takes to write it. So this is our exageostat software. This is a task graph. This is a 4x4 Cholesky factorization. The greens are factoring the diagonal blocks. The reds are applying the factors down the columns, and so forth. The blues are the gems to go across, update. And you can see that you don't have to just go down the diagonal. The width of this is the number of things that can be done concurrently. The height of it is the time that it takes. And this is a directed acyclic graph expression of all the dependencies that have to be respected in order to you know, get the mathematically correct result. This is software that was engineered by Sameh Abdullah. It has a synthetic generator, the likelihood estimator, and the predictor, which is like, you know, solving the Schur complement for the missing degrees of freedom, where you want data but you don't have measurements. It's called Krieging in statistics. And this has been implemented on many processor architectures on the left, as embedded in many of the world's leading systems on the right. So it's been implemented in a very portable way. And there again is the log likelihood function. The optimization that we use is NL-opt, which is from Steve Johnson at MIT. If you want more concurrency than what you get from linear algebra, you can carry out several of these optimizations in parallel independently, looking for the best fit, theta. That's somewhat wasteful, but you can shrink the time with extra cores if you have it. These are some of the fits that spatial statistics use on the left, and the right are our space-time. We used the top two in our Gordon Bell estimates, and we choose the rank by basically deciding if it turns out if the rank If the effective rank is greater than 2, you should keep it dense. If it's less than 2, you can win by sparsifying it. And these are structure-aware decisions. You don't know ahead of time what the rank of a given block will be until you've proceeded to that stage of the elimination. So it's adaptive, based on the estimated cost of working with that block. How to choose the precision is something that, again, was provided by Hyam and company in the 2022 Acta Numerica article, at least for matrix multiplications. There's still a lot of stability analysis needed for more intricate operations. But if your goal is to replace a matrix A by a hybrid precision equivalent such that the difference between the two, the Frobenius norm, is bounded by any precision you want, then the block size is going to be n sub t. And the way you choose the precision of any tile is to enforce this inequality, where this is the Frobenius norm of the tile, this is the Frobenius norm of the overall matrix, which, by the way, can be computed in a streaming way. You don't need to have the whole matrix living in memory at any point in time. And then this is the ratio of the two precisions in question. And you can generalize this to high, low, lower, lowest, and so forth in a hierarchy. And in the end, the matrix replaced with adaptive precision chosen blocks has a Frobenius norm, which is bounded for this two-level case by the high, the tight tolerance, high precision, Mach F. So this can be converted dynamically. And these are some results. This is, there's like 27 boxes on this, box and whisker plots. There are 3 different problems: weakly correlated, medium correlated, and strong correlated. There are 3 different parameters: the variance, the range, the smoothness, and within each box of correlation, strength, and parameter being found, there are 3 different algorithms. So the 3 different algorithms are dense double, mixed precision dense with full rank, mixed precision dense with also tile low rank. So the optimal algorithm, the most efficient algorithm is the one on the right, and you can judge from these box and whisker plots how well the statistics is served by cheating, if you will, on the energy. That's the interpretation of the box and whisker plots. And maybe of greater interest is the mean square prediction error at the unknown points for the 3 algorithms. The standard one, mixed precision and mixed precision with tile low rank. And, in the mean square sense, over the entire field of predicted values, they give approximately the same performance. But they don't give the same cost. This is on Fugaku, the Japanese A64FX machine, which up until about a year ago was the world's #1. It shows for a variety of algorithms and processor sizes, you can get 3 times less time for the same size problem, or 3 times greater size problem for the same time. And this was sort of an incompletely converged performance study because we had a lot of problems with our dynamic runtime system that assigns the work to these cores. It ended up taking a lot more memory by itself. So the algorithm, which is supposed to save you memory, starts taking a lot of memory, and that's something that we need to work more on. But anyway, it was an intermediate point showing the potential of the method, and these are 4 different covariances. 2 of them weak correlation, 2 of them strong correlation, showing if you don't use low rank, generalize to the low rank. To compete in Gordon Bell, you need to get people from the application domain to write about the significance of it. I won't read those. I'll go on to the last one, which is the 2023 paper, which was a seismic imaging problem. And scaling the memory wall goes back to, I think it was a 1986 paper, where the growing gap between processor strength and memory bandwidth was beginning to be observed. leading to now today as many as 3 or 4 levels cache and different kinds of high bandwidth memory, try to cover that growing gap. But a particular solution that has been pioneered recently by Cerebras, a Silicon Valley AI company out of California, which sold a large system to the G42 group in the United Arab Emirates, was to try to use this AI machine to do a basic imaging process used a lot in Saudi Arabia, namely find subterranean structures, again using algebraic compression. So this is not a multiple precision application. This is just a low rank application. We had to work with Cerebras engineers. It's sort of programming in assembly language. We took our algorithm that we ran on our own Cray, did all the science there, and then said, okay, now you guys show what performance we would get on your system. And this is the chip. It has only SRAM. There's no DRAM. Every byte of memory, every bit of memory is 6 transistors. They flip fast. They cost energy themselves, but the memory is near the cores. And so there's very little cost in data motion. There's no copper in this system. You know, when you shrink the system, it's the resistivity of the tiny copper vias that makes the modern processor inefficient. And this was what we were going after was improving the memory bandwidth. And this is the algorithm. This is the original. This is a matrix that's not square. It's not going to be factored. It's some observations in the frequency domain. It has to be multiplied against the vector many times. It has a low rank representation, which is adaptive in rank after some good Hilbert ordering to get good compression. And the product of that matrix on a vector can be executed in 2 phases with V's of the SVD and U's of the SVD applied separately, and a shuffle operation in between. And to get to sort of the climax, here we compare 1, 2, 3, 4, 5, 6, 7, 8 systems. There's 7 systems here. And you'll notice there's different numbers processors. So 6 Cerebras CS2s, 1 AMD, 2 NVIDIA A100s, 4 Fujitsu. The number of systems we picked, the number of nodes we picked of each system, rather, was as much as needed to put the problem in memory. A small problem, put it in memory. So it's a fair comparison for a same size problem. What you see here is roofline plots. These systems are sold saying, the peak floating point performance is this number of gigaflops. But if your problem isn't living in cache, then the performance you're going to see is the performance of moving the data in and out of the CPU, in and out of the registers and floating point units. So many of these systems are actually memory bandwidth bound. And the 6 Cerebras, there's the memory roof, and then there's the full compute. You want to drive the computation to the right, so you use the full compute and not just the memory bandwidth. These are some real data points on the Fugaku and the Frontier at Oak Ridge, and 2 points on this Cerebras system. We had 48 of them glued together. I think it was the largest group they've ever tied together. Normally, these are sold separately to do AI-like things. We have 2 measurements here because this one, because there's no cache, or put this way, because of the processors in memory nature of this architecture, it's necessary to reload things frequently. We didn't want to take credit for reloading things that other systems wouldn't have had to reload. So this is the fair number to compare with these. This is a very impressive number in terms of petabytes per second, but it's because of the limits of the architecture. So the relevant things to compare are these 3. And you can see that the Cerebras system, which costs about $100 million, is equal in memory bandwidth for this algorithm to the Fugaku, which costs $1 billion. So it's a factor of 10 savings in the architecture to get the same performance on this particular seismic problem. And again, two geophysicists and a previous geophysics Gordon Bell winner weighing in on us. And I like this quote from Mark Twain: "History does not repeat itself, but it often rhymes." And in 1989, the second year of Gordon Bell, it went to a seismic application running on the CN2, the Connection Machine 2. Maybe most of you weren't born. That was one of the earliest parallel machines. It was a machine designed for AI, but it ended up getting a lot of use on conventional science. In 2023, we went for Gordon Bell on a seismic application running on the CS2, a system designed for AI. So we thought that was poetic justice, but we didn't win. But at least we were able to call attention to a new class of algorithms. So to sort of come to the end, we're interested in targeting this algorithm infrastructure, providing a nice API for many applications on an ever extended and evolving class of architectures, all of which seem to be memory capacity or memory bandwidth limited. My conclusions recapped are that in all three of these orthogonal directions, HPC scientists are making great progress. And I think most of the people in this room, like me, are most interested in enabling the algorithmic kernels, whether they be sparse solves, direct solves, potential evaluations, whatever. Sustainable computing has two meanings. We compute sustainably, or at least as efficiently as possible, not computing more than necessary for a given scientific target, and we compute to support sustainability, renewable energy, affordable energy, climate predictions, and so forth. These are two of the sustainable development goals of the United Nations: responsible consumption and affordable energy. And you may be familiar with the goals. And, many universities are actually competing for their success in these goals in research, education, operations, outreach, and innovation in something called the Times Higher Education Impact Rankings. And that's actually one of the things that drives us as a university. So contributions are required up and down the software tool chain. This is a very narrow view of dense linear algebra here. Our group is called HICMA, Hierarchical Computations on Many Core Architectures. I think MOX is cool, but HICMA is the Arabic word for wisdom. So it was a conspired acronym. And if you're interested, let's talk. And we embedded the house logo in Sustainable Development Ring. And there are some references. And I can't thank you enough for the honor of your attention.
So thank you, David, for this very, very interesting talk. Is there any question? Paolo, please go ahead.
Really, thank you very much for this beautiful lecture. I think it motivates older and younger generation of researchers to look into HPC if they're not there yet. Really, thank you. My question is about something you mentioned, and maybe if there is more to say, is about randomized linear algebra, which is coming up through this fusion between machine learning and numerical analysis and computing. Is it, let's say, a technique that can improve the efficiency and the speed of calculations? What's your view about that?
Okay, so we looked at one narrow part of it, which is the randomized SVD by Gunnar Martinson and Halko, and who was the third author there? A very, very highly cited, Cyan paper. There are many experts in this domain. Laura Grigori is one that's contributed a lot. Ilse Ipsen has contributed a lot of algorithms beyond the SVD. I'm not an expert in the random linear algebra domain, but the typical paradigm is you find a random set of vectors that represents the full dimension, and in many cases of interest, that very small subspace of the full dimension contains enough information because of the fortunate decay of real physics, real biological system, and so forth. It looks to me to be a very appealing frontier. I would direct you to Laura and Ilse and many others for finding out what are some of the other frontiers besides the SVD. We just use the SVD sort of as a black box. It's good if you have a good prediction of the rank. If you don't have a good prediction of the rank ahead of time, you have to apply it, over and over again and keep increasing space, and that can be more expensive than eventually using the real thing. So, and again, let's distinguish random algorithms from random matrices. The expert there being Alan Edelman. Random matrices don't compress at all. So we're using random algorithms on matrices that are highly compressible, and that seems to be, maybe a 5 or so year thrust that is proving very fruitful. So, just an overview.
Is there any other question or comment, maybe from online? I do have very naive question.
Yeah.
So I was wondering if this mixed precision algorithms you have discussed can be employed somehow or can be exploited to design like a multi-level solvers, right? In an algebraic fashion, when you use low precision
I see what
to
you're
cook
saying.
up
Yeah,
the coarse
So
space.
instead of going from fine to coarse mesh,
Exactly.
go from low to high
precision
precision,
to
do
low precision.
almost all the work in low precision and get the answer in high precision in a small number of iterations. Yeah, I think that's a very good philosophy. Of course, that actually the classic iterative correction, Gauss elimination, does the NQ factorization in low and the residual evaluation high. But recently, maybe 5 years ago, Don Guerra and Nick Hyam. By the way, so many of you have heard, you just lost Nick Hyam this week. It's one of the most crushing things that has happened to me. I felt like I lost an intellectual father, even though he's younger than me. They cooked up a form of GM-res where many steps were meted out to different precisions, and I think there was even an inner outer with an inner which was compute intensive, which was lower, and an outer. But it was both the Krylov method and the preconditioner that were hierarchicalized in precision, and I think there's a lot of potential there. There's not a lot of theory. It's to me actually one of the most exciting things about mixed precision is that it means you can go back to your your favorite linear algebra book, and suddenly there's a lot more theory to do. Where can you let the precision flow without losing the precision in the high answer? The theorem I quoted by Hyam is only for really it's really effective for matrix multiply. When you factor, you could have some small precision getting amplified by division. Yeah, so there's a lot of theory to do there.
Thank you very much. Is there any other?
Oh, actually, one other thing is data compression. It's sort of similar to data compression. Climate people save petabytes of data from their double precision simulations, and they refuse often to let you apply lossy compression to it. And to be sure, a lot of energy went into finding the fully accurate thing. But a lot of the methods that are used in compression are sort of bit oriented, patterns in bits or polynomial fits. There's very little in the algebraic sense. If you store a field as a matrix, you may be able to to use these algebraic methods, not on the operator, but on the field itself. And that would, and if they're both stored in a block way, like low rank or mixed precision, then when you apply the operator to the data, you don't have to convert back from compressed. You can do all the arithmetic in the compressed form. So that's another, I think, interesting horizon for numerics.
Thank you. Yeah. If there are no further comments, I think we can have the coffee break, nice. Which is at the 6th floor in the meeting room. No, in the meeting room. Okay, and let's thanks again. Grazie.